Okay, welcome back. So now let's talk about graph representations in programming. Okay, so if we want to use graphs in our programs and our applications, then we need to find a way to represent these graphs numerically, okay, or using our different data structures. So let's say we have these two graphs here. We have an undirected graph and we have a directed graph, each with 6 nodes and 7 edges. So one way that we can represent these graphs is through what we call an incidence matrix. Okay? So in an incidence matrix, we have essentially a 2D matrix. Okay? So each row in an incidence matrix corresponds to one node. Okay? And each column corresponds to one edge. Okay? And say in an undirected graph, we see here that the edge 1, 2 has a value of 1. So the node 1 and the cell occupying node 1 and edge 1, 2 has a value of 1, which means that this edge is incident on node 1. So I can start from node 1 crossing to node 2 through this edge. And similarly, if I have an edge 1, 2 in an undirected graph, I can start from node 2 and go back to node 1. Okay? And if I have an edge 3, 5, then I expect that I have a 1 in the third row and the fifth row, because I can go from 3 to 5 and from 5 to 3. Okay? Now, in a directed graph, we make a distinction between the starting node and the end node of an edge. So if I have an edge from 1 to 2, then if I start at 1, this cell has a value of 1, while the terminal node 2 has a value of -1. And I do the same for every other edge in the graph. Okay? If I have an edge from 2 to 4, then the cell at row 2 has a value of 1, and the cell at row 4 has a value of -1. Okay? So when do we use this type of representation? If we have V nodes and E edges in a graph, then we can see that the number of entries, or the number of cells in the matrix, is V times E. Okay? But since we have E edges and we expect that for every edge only 2 cells are filled, then in the whole representation only 2 E entries are actually filled in the 2D matrix. Okay? So in general, this kind of representation is inefficient. We have a lot of cells that we don't actually need in our representation. Okay? So practically speaking, we don't use incidence matrices in code because they will take up a lot of unnecessary space, and they're typically used only for conceptual or mathematical analysis. Okay? Because it's easy to see when you have an edge which nodes are connected, but practically speaking, it's not efficient for us as programmers. Okay? So another representation that we can use is called an adjacency matrix. Okay? So in an adjacency matrix, it's again a 2D matrix, and now both our rows and our columns represent nodes in the graph. Okay? And what's the content of our matrix? So again, let's recall that in our first graph, we have an edge, say, from 1 to 2 and from 1 to 3. So if I look at the row 1, then I say that columns 2 and 3 of this row are filled because I have an edge from 1 to 2 and an edge from 1 to 3. Okay? So each row actually represents the initial node or the starting node, and each column represents a terminal node. And I mark a 1 when there's an edge from a starting node to an ending node. Okay? Now, in an undirected graph, we know that if I have an edge 1, 2, then I can actually go from 2 to 1 as well. So here, in row 2, then this cell, row 2, column 1, is actually filled because I can also get from node 2 to node 1 through an edge. And interestingly, if we have an undirected graph, then because of that property, that we can traverse edges in either direction, our adjacency matrix for undirected graphs is actually symmetric. Okay? So if we flip it along this diagonal, then both cells will actually be filled on either side. Okay? So if I have an edge from 2 to 4, then or rather from 4 to 2, then I know that I also have an edge from 2 to 4. Okay? Now, in a directed graph, that doesn't necessarily hold. So we know that, for example, in this graph, there's an edge from 1 to 2, but that doesn't mean that there's an edge from 2 to 1. So we see that the cell 1, 2 is filled, but the cell 2, 1 is not filled. Okay? So in a directed graph, it's possibly sparser because now we only specify a 1 in the cells which have directed edges. Okay? So even if we have 7 edges in both graphs, our adjacency matrix for the undirected graph actually has 14 cells filled, while only 7 cells are filled in our adjacency matrix for the directed representation. Okay? Now, a third way of representing our graphs is through an edge list. So literally, an edge list is a list of edges in the graph. Okay? So a list, or for example, a vector in C++ can contain the edges of our graph as, say, a pair data structure. Okay? So I have a set of ordered pairs here. In an undirected graph, again, if we have an edge from 1 to 2, we can say that there's also an edge from 2 to 1. So I can list 14 edges like I did for the adjacency matrix. While in my directed graph, then there are only 7 edges in my edge list. Okay? And each pair denotes an edge existing from A to B. But depending on the assumptions, for example, if I know that I'm dealing with an undirected graph, then possibly the connections from, say, 1 to 2 and 2 to 1 could be redundant. Okay? If I know that it's an undirected graph anyway, I could simply have one ordered pair representing both directions of the edge. And as long as I'm consistent with this notation, if I'm trying to find a path, if I locate just this pair 1, 2 in my edge list, then it should be able to function normally. Like, I can say that, okay, if I have this pair, then I can also get from 2 to 1. So as long as you're consistent with your notation in edge list, then you can actually shorten your undirected representation. Okay? And finally, we have our adjacency list representation. Okay? So an adjacency list is actually kind of a misnomer because it's more of a mapping or a hash table. Okay? So in our adjacency list, we have a mapping from our nodes to a list of nodes adjacent to the key. Okay? So our key is a node, and the value in the map is a list of nodes. Okay? And for example, in our first graph, 1 is connected to nodes 2 and 3. 4 is connected to nodes 2, 3, 5, and 6. So that's what we expect in the list, okay? So it maps to the list of nodes that it's adjacent to. 1 is adjacent to 2 and 3. 4 is adjacent to these 4 nodes, and so on, okay? And the same is true for the directed representation. For each node, we map it to the set of nodes that it's adjacent to. We see that 1 is adjacent to 2, okay? And 2 is adjacent to 3, 4, and 5. But 3 is actually not adjacent to any node because there is no edge going out from 3 to any other node. So we can see that here. 1 is adjacent to 2, 2 is adjacent to 3, 4, and 5, and 3, the list mapping to 3 is empty. Okay? Now, of course, when we use these data structures, we want to analyze the complexity of use for each representation. So, what are the operations that we can do when we have our graph representations? So, when we have our graphs, we want to be able to add an edge to the graph. We want to check if, say, an edge exists. We could possibly want to find all the neighbors of a specific node. And we also want to talk about how much space a representation occupies in computer memory. So, for an incidence matrix, it actually has generally the highest of any of the 4 representations that we used, okay? So, adding an edge in the other 3 representations is only a constant time operation. But for an incidence matrix, if you wanted to add an edge, then it would be an O of V operation, V being the number of vertices. Because if we added an edge, then we would add another column entirely. And we would have to locate. Okay, if I wanted to, say, add an edge from 2 to 5, then I would have to locate. Okay, which row represents that node 2, which row represents node 5, and so on. Okay, so trying to fill that column is an O of V operation. Now, if I wanted to check if an edge exists, so for an incidence matrix, that's O of E. Bakit? Kasi I have a sequence of edges in this axis, then I would have to look through each edge to see if this is the edge I'm looking for. Now, for the other representations, in adjacency matrix, if we wanted to check if an edge exists, that's only an O of 1 operation. Because what does it mean to check if an edge exists? So if I wanted to see that there's an edge from 2 to 4, then I would simply look at the cell 2, 4. Okay? And I would have either a value of 0 or a value of 1. 1 if the edge exists, and 0 otherwise. So it's a constant time operation. Now, in an edge list, it becomes an O of E operation. Bakit? Because we have a linear representation of our edges. So we would have to check each element of the edge to see if the edge is actually in the list or not. We don't place an ordering on the edges, so we have linear search. And for an adjacency list, then it actually depends on the degree of our starting node. Okay? So if I want to check if there's an edge from, say, 3 to 5, then say I check the list mapping to 3, there are 3 nodes adjacent to 3, so I would perform linear search on this list. Okay? So if this list has a length of 3 corresponding to the degree of this node. If I had a shorter list, for example, this list mapping to 6, then I'd only have to search one element to say that, okay, it's either in this list or not. But if I have a longer list, say node 4 has a degree of 4, so it would take a much longer time. Okay? So adjacency lists are faster in that regard if you have a sparser representation or a graph with less edges in general. Now, to find all the neighbors of a node, again, in an incidence matrix, if I wanted to see the neighbors of a node, I would have to look at all of the elements of a single row. So that's an O of E operation, wherein the length of any one row corresponds to the number of edges in the entire graph. For an adjacency matrix, to check all the neighbors of a node, it becomes an O of V operation, because for any one row, it has V elements, V being the number of nodes in the graph. For an edge list, again, we would search through this whole list to identify that. So it becomes an O of E operation again. And for an adjacency list, again, it would depend on the degree of our node. Okay? So it's essentially equivalent to finding or printing all the elements in that list. So it depends on the degree of the node, okay? Or it's proportional to the degree of the node we're searching for. And in terms of space complexity, we saw that the incidence matrix is a V times E dimensional graph, or a matrix. An adjacency matrix is V squared. An edge list has a length of E, and an adjacency list actually has V plus E, space complexity. What does that mean? So if I have, say, 6 nodes, then the keys would be of size, the set of keys would be of size 6, and the amount of space in our lists, the total space would be corresponding to the total number of edges. So it's V plus E. Or for example, in the undirected representation, I have 6 nodes, so that's V, and I have 2 times the number of edges in total in this union of lists. Okay? So that's 2E. So in general, it's O of V plus E. Okay? So when do we use each of these representations? In general, the 2 most common that you'll find when implementing graphs are the adjacency matrix and the adjacency list. Okay? So the adjacency matrix is typically used when we have a dense representation. If we have a lot of edges, then it's a lot easier to operate on an adjacency matrix. We can fill our matrix efficiently. Okay? A lot of these cells would be filled, so we have an efficient representation. But if we have a sparse representation, for example, our directed matrix here, we see that there's a lot of unused space in our adjacency matrix. So it actually becomes more efficient to represent this as an adjacency list. Okay? So either of these two are the representations that we typically use in our programs and algorithms. Okay? So in the next 2 videos, we'll be talking about our graph traversal algorithms.